Good morning. Welcome to the session of grade 11 Euclidean geometry. Before we start with the grade 11 work, we're going to do a revision on the previous grade's works. In this case, we are going to look at the properties of quadrilaterals. Now, a parallelogram. In a parallelogram, the following characteristics apply. The opposite sides are parallel, the opposite sides are equal, the opposite angles are equal, and the diagonals bisect each other. Obviously, the cointerior angles on the same side of the transversal are supplementary. The characteristics of a rectangle. Now, all the properties of a parallelogram also apply to a rectangle. However, the interior angles of a rectangle are equal to 90 degrees and the diagonals are equal. So the difference between the diagonals of a parallelogram and the diagonals of a rectangle is that the diagonals in a rectangle are equal and they bisect each other, where in a parallelogram they only bisect each other. The characteristics of a rhombus. Now, all the properties of a parallelogram are also applicable on a rhombus. However, all four sides are equal. In this case, opposite sides are equal. In a rhombus, all the sides are equal and the diagonals bisect each other at 90 degrees. And in this case, the diagonals also bisect the interior angles of a rhombus. So that angle would be equal to that, and that angle there will be equal to that. Opposite angles are equal and the diagonals bisect the interior angles of a rhombus. Right, in a square, all the properties of a parallelogram and a rectangle and a rhombus is applicable in a square. However, the interior angles are all equal to 90 degrees and the diagonals bisect the interior angles of a square. In a trapezium, one pair of parallel sides are equal. And in a kite, the adjacent sides are equal. That is equal to that side is equal to that side. The long diagonal bisects the short diagonal at 90 degrees. And in this case, we can see that if this is 90 degrees, then all the angles around the point are also equal to 90 degrees. And then the diagonals bisect the opposite angles. So in this case, A1 is equal to A2 and C1 is equal to C2. You need to know and understand the characteristics of quadrilaterals because you will use it to solve certain problems. Right, let's go back to the basics of your geometry. So we're going to go back to the grade 8 work. The angles on a straight line add up to 180 degrees. Or you can say the angles on a straight line are supplementary. If two straight lines intersect, then the vertically opposite angles are formed and they are equal. So in this case, A is equal to B and X is equal to Y. Complementary angles, that means X plus Y adds up to 90 degrees. In parallelograms, the following kind of angles exists. Here we get alternate angles exist. So if both angles are found on the inside of the parallel lines or on either side of the transversal, then they are called alternate angles. Cointerior angles exist. That means one angle is found on the inside, one found on the outside on the same side of the transversal. So we can get alternate angles, as I've demonstrated. That is equal to that and that is equal to that. We get corresponding angles where that is equal to that and that is equal to that. And we can also get cointerior angles where that angle plus that angle adds up to 180 degrees. Now, cointerior angles are both angles found on the inside of the parallel lines on the same side of the transversal, and they add up to 180 degrees. If we look at the triangle, then the interior angles of a triangle will add up to 180 degrees. the sum of the angles of a triangle add up to 180 degrees. If the two sides are equal, then the angles opposite equal sides are equal. So in this case, if two sides are equal, we are busy with an isosceles triangle, and the angles opposite equal sides are equal. In a triangle, the exterior angle is equal to the sum of the opposite interior angles. And in a equilateral triangle, all three sides are equal, then all three interior angles will be equal to 60 degrees. That is an equilateral triangle. Right, let's look at the revision of the triangle. We have done part of this on the previous page. We said, what is isosceles triangle? It's when two sides are equal. If two sides are equal, then the angles opposite the equal sides will be equal. If three sides are equal, that means it's equilateral, and then each of the interior angles will equal to 60 degrees. In a triangle, the sum of the interior angles add up to 180 degrees, and the exterior angle is equal to the sum of the opposite interior angles. And if it's a right angle triangle, then Pythagoras Theorem applies. Opposite 90 degrees, we've got AC. So AC squared is equal to AB squared plus BC squared. Right. Congruency. Now congruency, the symbol for congruency is three horizontal lines. That is the symbol for congruency. And when will two triangles be congruent? If the following conditions exist. If this side is equal to this side, that side is equal to that side, and that side is equal to that side. If the condition of side, side, side occurs, then the two triangles are congruent. Now congruency means that the two triangles will fit exactly over each other, and all the corresponding sides and corresponding angles are equal. So opposite three sides, I've got this angle. Opposite three sides, I've got that angle. Opposite one side, I've got that angle. Opposite one side, I've got that angle. Opposite two sides, I've got that triangle. Opposite two sides, I've got that triangle. So if two triangles are congruent, then they are equal in all respects. All three sides of one is equal to all three sides of the other, and the corresponding angles of one are equal to the corresponding angles of another. Another case of congruency exists if I've got two sides and included angle. So if that side is equal to that side is equal to that side, and that angle is equal to that, then the case of side, angle, side exists, then the two triangles will be congruent, which means they will be equal in all respects. The third case of congruency is when two angles and a side is equal to two angles of a side of another triangle. Then angle, angle, side exists, then the two triangles will be equal in all respects, and therefore they will be congruent. Right, the fourth case of congruency is right angle, hypotenuse, and side. If the right angle of one triangle is equal to the right angle of another, if the hypotenuse of one triangle is equal to the hypotenuse of another, and if one side of a triangle is equal to one side of another, then the two triangles are congruent, and then the case of congruency is right angle, hypotenuse, and side. If that case exists, then the two triangles will be identical. That means all three sides of one is equal to all three sides of the other, and the corresponding angles of one is equal to the corresponding angles of another. The midpoint theorem says that if a line segment joins the midpoint of two sides of the triangle, then it will be parallel to the third side, and it will be equal to half the length of the third side. So if B is the midpoint of AD and C is the midpoint of AE, then we can say AB is equal to BD and AC is equal to CE. Then BC will be parallel to DE, and BC is equal to the half the length of it. This is the midpoint theorem. Now the converse of the midpoint theorem states, if a line segment is drawn from the midpoint of one side parallel to the second, then it will bisect the third. The Proportionality Theorem says the following, that if a line is drawn parallel to one side of the triangle, then it divides the sides in the same proportion. Then PQ over QS is equal to PR over RT. This is called the Proportionality Theorem, and this theorem is done in grade 12. Right, let's look at grade 11 circle geometry. The following theorems need to be studied. You need to learn the theorem and you need to be able to apply the theorem. There are certain proofs that need to be proven, but in this case, let's just go through the theorems. Now, a line drawn from the center of the circle to the midpoint of the chord will be perpendicular to the chord. Now, the converse also applies, that a line drawn from the center of the circle perpendicular to the chord will bisect the chord. That would be the converse. Now, the angle at the center of the circle is twice the angle at the circumference of the circle if it is subtended by the same arc. So this arc subtends this angle at the center of the circle. This arc subtends this angle at the circumference of the circle. Now, the angle at the center of the circle is twice the angle at the circumference if it is subtended by the same arc. Now, this arc here subtends this angle at the center of the circle. This arc here subtends the angle at the circumference. Now, the angle at the center is twice the angle at the circumference because it's subtended by the arc AB. Number 3, a diameter subtends an angle of 90 degrees at the circumference. Now, if a line subtends an angle of 90 degrees to the circumference, the line is a diameter, and that's the converse of this theorem. Now, if this arc subtends this angle at the circumference, and this arc subtends this angle at the circumference, then we can say the same arc of a circle subtends equal angles at the circumference of the circle. All right, let's look at cyclic quadrilaterals. Now, a cyclic quadrilateral is when a four-sided figure is drawn in a circle and the vertices of the four-sided figure lie on the circumference of the circle. So in this case, because this here is a cyclic quad, we can say that x plus y is equal to 180 degrees. Opposite angles of a cyclic quad is supplementary. Now, the converse says, if the opposite angles of a cyclic quad are supplementary, of a quadrilateral are supplementary, then the quadrilateral will be cyclic. The other theorem says, if the exterior angle of a cyclic quad is equal to the opposite interior angle. Now, if it's a quadrilateral and the exterior angle is equal to the opposite interior angle, then that quadrilateral will be a cyclic quad. And another way to prove it's a cyclic quad, if a line segment subtends equal angles on the same side, then the 4 points are concyclic and it forms a cyclic quad. When it comes to tangents, there are 3 theorems. Remember, the radius is perpendicular to a tangent. If that is a radius and that's a tangent, then the angle formed is 90 degrees. The converse says, if this here is the radius and the angle formed is 90 degrees to a line touching the circle, then that line is a tangent. The other tangent theorems state that if tangents are drawn from a point outside the circle, then they are equal in length. So if 2 tangents are joined from the point P outside the circle, then we can say AP is equal to BP. Right, and 9. The angle between the tangent and the chord is equal to the angle in the alternate segment. So in this case, that angle there is equal to this angle here. And the converse says, if the angle between a chord and a line is equal to the angle in the alternate segment, then the line is a tangent. So to prove a tangent, we just got to prove that the line drawn from the center of the circle is perpendicular to the line is a tangent, or we can prove that if the angle between we can prove that if the angle between the chord and the line is equal to the angle in the alternate segment, then that line will be a tangent. Now just remember, when we make use of theorems, we do not have to state the full theorem. We can use an abbreviation for it. Now, if you look at your mathematics guidelines, in Euclidean geometry, there is a page of acceptable reasons for specific theorems. For example, if AB is parallel to CD, then the corresponding angles are equal. The abbreviated reason for that is corresponding angles AB is parallel to CD. If we're going to look at the grade 11 theorems, and we want to state that the tangent to a circle is perpendicular to the radius of a circle at the point of contact, then we can just say that the tangent is perpendicular to the radius, or the tangent is perpendicular to the diameter. That is the acceptable reason for this theorem. Or an angle subtended by an arc at the center of a circle is double the angle subtended by the same arc of a circle. We can say angle at the center is 2 times the angle at the circumference. Okay, let us look at solving geometrical problems. It is very important to analyze the required to prove. We've got to look at what do they want in the question. We've got to look for keywords. For example, if they say O is the center of the circle, then there's 5 theorems that we can apply. If they say it's a cyclic quad, we can apply 3 theorems. If they say it is a tangent, then we can look for 3 theorems that we could possibly apply. Right, and then remember, you must always do a rough proof, and then you can rewrite the formal proof. Now, if they tell you that there are parallel lines, then 3 different types of angles exist. Alternate angles, that is, both angles are found on the inside, on either side of the transversal. That's alternate angles. Or one angle is found on the inside, one found on the outside, on the same side of the transversal. That is corresponding angles. And cointerior angles, the interior angles add up to 180 degrees. Both angles are found on the inside of the parallel lines. They are not equal, but the sum of the angles is equal to 180 degrees. That is cointerior angles. If they ask us to prove parallel lines, then we either prove that A is equal to B. That means alternate angles are equal. Or we can prove that A is equal to D. That means corresponding angles are equal. Or we can prove that B plus C is equal to 180 degrees. That is, cointerior angles exist. So if we have to prove that 2 lines are parallel, then we can prove that alternate angles are equal, or corresponding angles are equal, or cointerior angles exist. Okay, the angle or line bisectors. If they say to you BD bisects angle ABC, then we can say B1 is equal to B2. Or if they say CD bisects AB, then we know that AE is equal to EB. So then BD is a bisector of the angle, and CD is a bisector of a line segment. If they mention that angle B is equal to angle C, then we can deduce that AB is equal to AC. If they say to us that AB is equal to AC, then we know that the angles opposite those equal sides are equal, therefore angle B is equal to angle C. If we are given a triangle, we know that the exterior angle of a triangle is equal to the sum of the opposite interior angles. So we know that angle C1 is equal to angle A plus angle B. But if it's a triangle, we also know that the interior angles add up to 180. So angle A plus angle B plus angle C2 is equal to 180 degrees. If they give a triangle where 3 sides are equal, we know it's equilateral. And in an equilateral triangle, the interior angles are each equal to 60 degrees. If they give each of the angles equal to 60 degrees in a triangle, then we know that the sides opposite those equal angles are equal, and therefore it is an equilateral triangle. Now, we did mention that there are certain key words that we need to look for. But let's just have a look at the following. If they say to you, prove that AC is equal to CB, what do we need to prove? If we prove that angle C1 is 90, or that angle C2 is 90 degrees, then we know that a line drawn from the center of a circle perpendicular to the chord will bisect the chord. Then we would have proven that AC is equal to CB. If we have to prove that AB is equal to AC, all we need to prove is that the angles opposite the equal sides are equal. We need to prove that angle B is equal to angle C, therefore AB is equal to AC. And to prove that AD is equal to DB, we just need to prove that these two triangles are congruent. So if these two triangles are congruent, then we know that AD is equal to DB. Now, the key words. If they mention that O is the center of the circle, then there are basically 5 theorems that we can apply. We can look at the following. We can say if O is the center of the circle, we look for the angle at the center of the circle is twice the angle at the circumference. Or the angle at the center of the circle is twice the angle at the circumference if it's subtended by the same arc. This arc subtends this angle at the center. This arc subtends this angle at the circumference. Angle at the center is twice the angle at the circumference. Or this arc subtends this angle at the center. This arc subtends this angle at the circumference. The angle at the center is twice the angle at the circumference if it's subtended by the same arc. The other theorem that we can make use of, if they say O is the center of the circle, then we know a line drawn from the center of the circle perpendicular to the chord bisects the chord. Or a line drawn from the center of the circle to the midpoint of the chord is perpendicular to the chord. If they say that O is the center of the circle, then we can look for equal radii. The line drawn from the center of the circle to the circumference is equal to the line from the center of the circle to the circumference. If these two sides are equal, then the angles opposite those equal sides will also be equal. We can also look for the radius tangent theorem. If the radius is drawn to a tangent, the angle formed is 90 degrees. If a radius forms an angle of 90 degrees to a line touching the circle, then that line is a tangent. And the last one that we look for is that if a line is drawn through the center of the circle, it subtends an angle of 90 degrees at the circumference of the circle. AB is the diameter, and it subtends an angle of 90 degrees at the circumference. Angles in the same segment, right. So in this case, you can see BC, the arc BC subtends A, BC subtends D. So equal arcs subtend equal angles at the circumference. Arc AD subtends angle B, arc AD subtends angle C, so angle B is equal to angle C. Right, if we look at chords in a circle, we know that AB will subtend angle D1 and BC subtends angle D2. Then D1 will be equal to D2 because equal chords subtend equal angles in the same segment. And equal chords subtend equal angles in equal circles. That means if the radius of this circle is equal to the radius of that circle, and BC is equal to DE, then BC subtends angle A in this circle, and DE subtends angle F in this circle, then A will be equal to F because they're both subtended by equal chords in equal circles. Right. When they mention the word cyclic quad, then we can make use of the following theorems. If it's a cyclic quad, then we know opposite angles are supplementary. That means angle A plus angle C is equal to 180 degrees. And we know that angle B plus angle D is equal to 180 degrees. If they mention a cyclic quad, we know the exterior angle is equal to the opposite interior angle. So in this case, we know that M2 is equal to angle P. Or if they say it's a cyclic quad, then we know that FG subtends angle E1 and FG subtends angle H1. Therefore, F1 is equal to H1. If it's a cyclic quad, we know that GH subtends F2 and GH subtends E2. Then F2 is equal to E2. Or, in this case, EF subtends angle H2 and EF subtends angle G2. Then E2 is equal to G2. Equal chords subtend equal angles on the same side of it. If we have to prove a cyclic quad, then we can either prove that one pair of opposite angles are supplementary. We must either prove that A plus C is equal to 180 degrees, or angle B plus angle D is equal to 180 degrees. Or we can prove that the exterior angle is equal to the opposite interior angle, or we can prove a line segment subtends equal angles on the same side, therefore it's a cyclic quad. Right, once again, to prove this is a cyclic quad, we can prove that either angle A1 plus 2 plus angle C2 plus 3 is equal to 180 degrees, or angle B1 plus 2 plus D1 plus 2 is equal to 180 degrees. That means opposite angles are supplementary. Or we can prove that angle C1 is equal to angle A1 plus A2. The exterior angle is equal to the opposite interior angle. Or we can prove, if we prove that angle A2 is equal to D1, then it's a cyclic quad because BC subtends equal angles on the same side. Or if we can prove that angle D2 is equal to C3, then AB subtends equal angles on the same side, therefore it's a cyclic quad. So there are other conditions that we can also apply. If DC subtends A1 and DC subtends B2, if A1 is equal to B2, it's a cyclic quad because DC subtends equal angles on the same side. So to prove a cyclic quad, you can make use of any one of those theorems. To prove a tangent, if they ask you to prove that a certain line is a tangent, then all we need to prove is that the radius is perpendicular to the line. If the radius is perpendicular to the line is a tangent. Or if they say that's a radius and that's a tangent, we know the angle formed is 90 degrees. If we draw tangents from a point outside the circle, then the two lines are equal in length, and therefore the angles opposite the equal sides will be equal. And the Chord theorem, if the angle between the tangent and the chord is equal to the angle in the alternate segment, then we know it is a tangent. And how do we prove a tangent? Right, if that is a line touching the circle and we can prove that that's 90 degrees, then that will be a tangent. If this here is a line touching the circle and we can prove that angle C1 is equal to A, then DCE will be a tangent. Or if this here is an imaginary circle and we've got to prove that ABC is a tangent to BDE, we have to prove that B1 is equal to E. If B1 is equal to E, then we can say ABC is a tangent through the points B, D, and E. Right, this brings us to the end of the theory part of the questions. We're going to take a 10-minute break, and then we will do the past paper questions where we will apply these theorems in the questions. Welcome back to the second session of grade 11 Euclidean geometry. In this section in this time slot, we will focus on the past paper questions. This question comes from the November 2014 paper. Now remember, when you get a question, read through the question and look for key words. Two circles in the diagram have a common tangent. Now, tangent is a key word. Now, if x or y is a tangent, then we can make use of the tangent theorems. That means the angle between the tangent and the chord is equal to the angle of the alternate segment. Or if a line is drawn from the center of the circle to a tangent, the angle formed is 90 degrees. Okay. The next one, they don't say that anything here is the center of the circle, so we can use the angle between the tangent and the chord is equal to the angle of the alternate segment. So, if this here is x, then, and we're looking at this triangle here, then the angle between the tangent and the chord is equal to the angle in the alternate segment. And if we look at the big circle here, the angle between the tangent and the chord is equal to the angle in the alternate segment. In the small circle, we are looking at this triangle, and x is equal to this. In the big circle, we are looking at this triangle, and x is equal to this. They say that chord STQ is a tangent to the small circle, where T is the point of contact. Chord RTP, R4 is equal to x, and they say R2 is equal to y. The question says, give reasons for the statements below. Why is T3 equal to x? It's the tan chord theorem. Remember, we said that we can make use of the abbreviated acceptable reasons for the theorems. And why is P1 equal to x? Also, the angle between the tangent and the chord. Let me just draw this here. In the small circle, we are looking at this triangle here. And the angle between the tangent and the chord is equal to the angle in the alternate segment. If we look at the bigger triangle, in the bigger circle, we are looking at this triangle here. And that's why the angle between the tangent and the chord is equal to the angle in the alternate segment. In this case, we can say P1 is equal to x, and we are busy with the tan chord theorem. And the next question is, why is WT parallel to that? Now you can see P1 is x and T3 is x. Corresponding angles are formed. In this case, we can say P1 is x and T3 is equal to x. Corresponding angles are formed, therefore the lines are parallel. They say, why is WT parallel to SP? Because T3 is equal to P1, which is equal to x. Corresponding angles are formed. And that's why the two lines are parallel. In the next question, they say to you, prove y is S1 equal to y. In this triangle here, this angle here is equal to y. And if we look at this triangle here, then PQ subtends equal angles on the same side. So therefore that is also equal to y. Because PQ subtends y, which is R2, PQ subtends S1, which is also equal to y. So they say y is S1 equal to y because PQ subtends equal angles. The next question is, they asked, why is T2 equal to y? Why is this here equal to y? Now, because that is x and that is x, we proved that that line is parallel. Because P1 was equal to T3, which is equal to x, we deduced that that line is parallel to that. Now, S1 is y, and that will be equal to T2. So T2 is y, because alternate angles are formed. So why is T2 equal to y? Because T2 is equal to S1, which is equal to y, because alternate angles are formed, because the lines SP is parallel to WT, and that we already proved. Right, let's look at the next question. This paper is the DBE grade 12 exemplar paper, which is the June paper in 2014. They say, give reasons for your statements in questions 8, 9 and 10. Question 8, complete the following statement. The angle between the tangent and the chord at the point of contact is equal to the angle in the alternate segment. Right. The next one, in the diagram, A, B, C, D, and E are points on the circumference of the circle such that AE is parallel to BC, BE and CD meet in F, and GBH is a tangent to the circle. B1 is 68 degrees and F is equal to 20 degrees. Right. So the most important thing here is to be able to look at your key concepts. Now they say to you that this here is a tangent, and we know that the angle between the tangent and the chord is equal to the angle in the alternate segment. So this must be 68 degrees. We also know that this line is parallel to this line, so if that is 68 degrees, then this here is 68 degrees alternate angles. And we know that this here is a cyclic quad, so the exterior angle is equal to the opposite interior angle. And we know that if this here is 20, this is 68, then this here will be 88 degrees. It is the exterior angle of a triangle. And we know if this is 88 degrees, then this here will be 92 degrees, because opposite angles of a cyclic quad are supplementary. Right, so that is just going through the theorems and applying certain things. Let us look at the question. They want E1. So we could say E1 is equal to B1, which is 68 degrees, is equal to B1, which is 68 degrees, and the reason is the tan chord theorem. It is very important that you are able to state your theorems and then apply your theorems. Remember, your reason can be written in the abbreviated form, and it can only be the reasons that is found in the exam guidelines. We now need to determine B3. Now, because that is 68 degrees and that line is parallel to that line, this B3 must also be 68 degrees. So B3 is equal to angle E1, which is equal to 68 degrees, and that is alternate angles because the two lines AE is parallel to BC. The next question, we need to determine D1. Now, because this here is a cyclic quad, D1 is equal to this angle here, which is 68 degrees. So we can say D1 is equal to angle B3, which is equal to 68 degrees, the exterior angle of a cyclic quad. Right, then we are going to do angle E2. E2 is this one here. Now remember, E2 is the exterior angle of a triangle. So E2 is equal to this angle plus this angle, which is equal to 88 degrees. So E2 is equal to 88 degrees, and the reason is the exterior angle of a triangle. So 20 plus 68 gives you 88, E2 is equal to 88 degrees. And now we got to work out C. Now if this here is 88 degrees, we know this here is a cyclic quad and opposite angles are supplementary. So if this here is 92 degrees and that is 88 degrees, then they add up to 180. So angle C is equal to 92 degrees, opposite angles of a cyclic quad are supplementary. Right, the next question comes from the November 2014 paper. In this question, they say, give reasons for your statements in questions 8, 9, and 10. Question 8. In the diagram, O is the center of the circle, passing through the points A, B, and C. CAB is 48 degrees, that is, this COB is equal to X, and C2 is equal to Y. Now, because they say O is the center of the circle, there are 5 theorems that we can apply. The angle at the center of the circle is twice the angle at the circumference, so this here should be 96 degrees. And because O is the center of the circle, these OC and OB are radii, and that means that the base angles are equal. So if this here is 96 degrees, then this here, C2, is 180 degrees minus 96 degrees, which is equal to 84 degrees, and divided by 2 because the base angles are equal. So in this case, if this here is 96, if it is 84, then it would be 42 degrees there and 42 degrees there. Right, let's quickly have a look. They want X. So we can say X here is equal to 96 degrees. The reason is the angle at the center of the circle is 2 times the angle at the circumference of the circle. Now if this is 96 degrees, remember that is equal to that, the radii, so the angles opposite equal sides are equal. So Y is equal to 180 degrees minus 96 degrees divided by 2. So that is equal to 84 divided by 2, which is 42 degrees. Because OC is equal to OB radii. Okay, the other theorems that we could have tried to apply is that the radius is perpendicular to a tangent. That's not applicable. And another theorem where O is the center of the circle, the line drawn from the center of the circle perpendicular to the chord bisects the chord, and it's not applicable. Or a line drawn from the center of the circle to the midpoint of the chord is perpendicular, not applicable. Right, 8.2. In the diagram, they say O is the center of the circle passing through the points A, B, C, D. AOD is a straight line. They say F here is the midpoint of the chord AB, and this here is 30 degrees, and OF is joined. Right. Here they say we need to find the size of F1. Now a line drawn from the center of the circle to the midpoint of the chord is perpendicular to the chord. So F1 is equal to 90 degrees. We can say a line drawn from the center to the midpoint of the chord. Right, the next one, we've got to prove that angle AB, we've got to find angle ABC. Now this here is a cyclic quad, and opposite angles are supplementary. So if that is 30 degrees, this should be 150 degrees because of the cyclic quad theorem. So ABC is equal to 150 degrees. Opposite angles of a cyclic quad are supplementary. Right. The next question comes from the February-March 2016 paper. Question 8. In the diagram below, the tangent KT to the circle at K is parallel to the chord NM. NT cuts the circle at L. Triangle KML is drawn. M2 is equal to 40 degrees and MKT is equal to 84 degrees. Determined, giving reasons, the size of K2. Now, if we can have a look here, they say this here is a tangent. Now the angle between the tangent and the chord is equal to the angle in the alternate segment, so this here is 40 degrees. The angle between the tangent and the chord is equal to the angle in the alternate segment. Now if the whole thing is 84 degrees and that is 40 degrees, the remainder is 44 degrees. 44 plus 40 gives you 84. Now ML subtends 44 degrees, so it will subtend 44 degrees here. And because this line here is parallel to this, if this here is 84 degrees, then that must be 84 degrees alternate angles. Now let's answer the question. Determine giving reasons the size of K2. Right, so K2 is equal to M2 is equal to 40 degrees, and here we've got the tan chord theorem. Now we need to work out N1. Now remember, N1 is equal to K1. So we're first going to say that N1 is equal to K1, which is equal to 84 minus 40, which is 44 degrees. And the reason is ML subtends equal angles on the same side. And the reason is ML subtends equal angles on the same side. Right. Now we need to work out angle T. Now, to be able to work out angle T, we can say that N1 and angle T forms alternate angles because the two lines are parallel. So angle T is equal to N1 is equal to 44 degrees, and the reason is alternate angles because KT is parallel to NM. Now we've got to work out L2. Now if this here is 44 degrees and that is 40 degrees, then L2 is the exterior angle of the triangle and it's equal to 40 plus 44, which is 84 degrees. So L2 is equal to 84 degrees, and the reason is the exterior angle of a triangle is equal to the sum of the opposite interior angles. And now we've got to work out L1. Now we know that the interior angles of a triangle add up to 180 degrees. So if this here is the triangle here, we know that each of those angles there will add up to 180 degrees. So we can say that 84 plus 84 it's 168, and the remainder is 12 degrees. So L1 is equal to 12 degrees because the sum of the interior angles of a triangle add up to 180 degrees. 12 plus 84 plus 84 will give you 180, the interior angles of a triangle add up to 180 degrees. Let's look at the February-March 2016 paper. They say in the diagram below, A, B, and DC are chords of a circle. E is the point on AB such that BCDE is a parallelogram, and DAE is equal to 2x plus 40 degrees. Calculate, giving reasons, the value of x. Now, because this here is a parallelogram, we know that the opposite angles are equal. So here we can say that angle E is equal to angle C, which is equal to 108 degrees. Opposite angles of a parallelogram are equal. And we know that the opposite this here is a cyclic quad, and the opposite angles of a cyclic quadrilateral are supplementary. So we know that angle A plus angle C is equal to 180 degrees. Opposite angles of a cyclic quad are supplementary. So here we say 2x plus 40 degrees plus 108 degrees is equal to 180 degrees. So 2x is equal to 180 minus 148, which is equal to 32 degrees. Therefore, x is equal to 16 degrees. Let's go again. We said 180 minus 148 is equal to 32. If you divide both sides by 2, then x is equal to 16 degrees. Right. We are now looking at the November 2015 paper, the national paper. They say in this case we've got to complete the following theorems. Now, the angle subtended by a chord at the center of the circle is 2 times the angle at the subtended by the same chord at the circumference of the circle. So it's 2 times or twice is what we need to fill in. And in this case, we have to prove the theorem that angle A plus angle C is equal to 180 degrees. Now, just a quick reminder, there are 4 proofs that you need to study. The 4 proofs are the following. You need to prove the following. If a line drawn from the center of the circle perpendicular to the chord will bisect the chord. The angle at the center of the circle is twice the angle at the circumference of the circle if it's subtended by the same arc. Or we've got to prove that opposite angles of a cyclic quadrilateral are supplementary, or you've got to prove that the angle between the tangent and the chord is equal to the angle in the alternate segment. So those are the proofs of the theorems that you need to study for in grade 11. Now let's just quickly have a look at this one. The proof here, we can write down statement and reason. We can say that angle O2 is twice angle C. O2 is equal to twice angle C. Angle at the center equals 2 times the angle at the circumference. And similarly, we can say that angle O1 is equal to 2 times angle A. Angle at the center equals 2 times the angle at the circumference. But we know that angle O1 plus angle O2 is equal to 360 degrees. O1 plus O2 is 360 degrees, angles around a point. Therefore, angle twice angle C plus twice angle A is equal to 360 degrees. Therefore, twice angle C plus angle A is equal to 360 degrees. Therefore, angle C plus angle A is equal to 180 degrees, and therefore you proved the question, which says that angle A plus angle C is equal to 180 degrees. So this here is a proof in your textbooks that you just need to study. Right, the next question comes from the November 2015 paper. It says, in the diagram below, CD is a common chord to the two circles. The straight lines ADE and BCF are drawn. Chords AB and EF are drawn. Prove that EF is parallel to AB. I'm going to prove that that is parallel to that. Now, when will two lines be parallel? Two lines will be parallel if the alternate or corresponding angles exist. Alternate angles, corresponding angles, or cointerior angles exist. So we can say that angle C1, let's call that X, is equal to angle E, which is equal to X. The exterior angle of a cyclic quad is equal to the opposite interior angle. But we also know that this here is a cyclic quad. We know that this here is a cyclic quad, and opposite angles are supplementary. So this here is 180 degrees minus X. Now, if this is 180 degrees minus X and this is X, then co-interior angles exist, because that plus that adds up to 180. Therefore, the two lines will be parallel. Okay, so to set this out, we're going to say angle C1, let C1 equal to, let C1 equal to X. So we're going to say C1 is equal to angle E is equal to X, exterior angle of a cyclic quad. But we can say that angle A plus angle C is equal to 180 degrees. Opposite angles of cyclic quad are supplementary. So in this case, we can say that angle A is equal to 180 degrees minus X. And then we can say that angle A plus angle E is equal to 180 degrees minus X plus X, which is equal to 180 degrees. And therefore, AB is parallel to FE. We can say co-interior angles exist. Because angle A plus angle E adds up to 180 degrees, the two lines are parallel because co-interior angles exist. Right. We are now going to move on to the February-March 2015 paper. The first thing that I need to do is to look for key words or key concepts. It says, in the diagram below, the circle with center O passes through A, B, C, and D. Now, if O is the center of the circle, then we got to make use of the 5 theorems. The angle at the center of the circle is twice the angle at the circumference of the circle, if it's subtended by the same arc BC. So BC subtends O1 and BC subtends angle D. So if this here is 110 degrees, then this here will be 55 degrees. Angle at the center is twice the angle at the circumference. We also know that if this is the angle at the center of the circle, then these two are radii. So if that is 110 degrees, then this here, that angle there and that angle there are equal because of radii. So 180 minus 110 is 70. So this is 35 degrees here, and the whole thing here is 35 degrees. The base angles are equal. The other theorems that we can apply, that a line drawn from the center of the circle to the midpoint of the chord is perpendicular. It's not applicable. The line drawn from the center of the circle perpendicular to the chord will bisect the chord. That's also not applicable. So we are left with the angle at the center of the circle is twice the angle at the circumference. And if O is the center of the circle, then these two are radii. It means the angles opposite equal sides are equal. The first question is, we need to work out angle D. The further instruction says that AB is parallel to DC. Now remember, if AB is parallel to DC, then we can say alternate and corresponding and cointerior angles exist. And if BOC is equal to 110 degrees, it's given, then there are chords ACBD, they intersect at E, and EO, BOC, O and BC are joined. So what is angle D? Angle D is equal to 55 degrees. Angle at the center is equal to 2 times angle at the circumference. So we've already proved that. To work out D, angle D, we said it's angle, if this is 110, then that is 55, because arc BC subtends this angle at the center, arc BC subtends this angle at the circumference, angle at the center twice angle at the circumference, D is 55 degrees, because angle at the center is twice angle at the circumference. Then we need to work out angle A. Now we know that BC subtends 55 degrees, so BC will also subtend 55 degrees here. So we can say A is equal to angle D is equal to 55 degrees, because BC subtends equal angles at the circumference. Right, and then we've got to work out E2. Now, to work out E2 is this angle here. What is further given here? We know that that line is parallel to that line. So we know that if this angle is 55 degrees, then this angle here is 55 degrees. And if that is 55, that is 55, then this E2 must be 110. Exterior angle of a triangle is equal to the sum of the opposite interior angles. So what is E2 equal to? So we're first going to say that angle A is equal to angle C2 plus 3, C2 plus 3, which is equal to 55 degrees, alternate angles. We said if that is 55 degrees, then that there is 55 degrees. And then we can say that angle E2 is equal to 110 degrees exterior angle of a triangle. Right, let's quickly have a look again. If that there is 55 degrees and that there is 55 degrees, then E2 is equal to that plus that, which is 110 degrees. So that's your final answer. Now we've got to prove that BEOC is a cyclic quad. We've got to prove that BEOC is a cyclic quad. You can see that BC subtends 110 and BC subtends 110. So therefore we can say, why is it a cyclic quad? Because BC subtends equal angles on the same side. Therefore BEOC is a cyclic quad. Okay, once again, BC subtends O1, which is 110, subtends E2, which is equal to 110, and therefore, because BC subtends equal angles on the same side, BEOC is a cyclic quad. Okay. We are now going to do the DBE 2015 paper, which is the June national paper for grade 12. They say, question 8, in the diagram, A, C, D are points, is drawn with points A and D on the circumference. There's A and D is found on the circumference of the circle. CD cuts the circle at B. P is a point on AD, with CP the bisector. Now CP is the bisector of ACD. So if that is 25 degrees, then that there is 25 degrees. They say AT is equal to AP. Here they say that AT is equal to AP. And ATP is equal to 65 degrees, and PCD is equal to 25 degrees. Okay, so what is P2 equal to? If AT is equal to AP, then this here is also equal to 65 degrees, equal angles, opposite equal sides. So PT is equal to 65 degrees, because AT is equal to AP. Now we've got to determine angle D. Now to determine angle D, we know that 65 is the exterior angle of a triangle, and it's equal to 25 degrees plus 40 degrees. So 65 is equal to 25 plus 40, so D must be 40. D is equal to 40 degrees, and the reason for that is P2 is equal to 65 degrees, therefore exterior angle of a triangle is equal to the sum of the opposite interior angles. And then we've got to work out A1. Now this here is a tangent, so the angle A1 must equal to angle D, tan chord theorem. So A1 is equal to 40 degrees. A1 is equal to 40 degrees, which is equal to angle D, and this here is the tan chord theorem. The question is CA a tangent to the circle ABD? The question is CA a tangent to the circle ABD? Yes, it is a tangent, because the angle between the tangent and the chord is equal to the angle in the alternate segment. Right, so here we can say angle A1 is equal to angle D is equal to 40 degrees. Therefore, it is the converse of tan chord theorem. The angle between the tangent between a chord and a line is equal to the angle alternate segment. Therefore, AC is a tangent. Right. We know that we proved that A1 is equal to D, which is equal to 40 degrees. Therefore, we can say that AC is a tangent, because the converse of the tan chord theorem applies. Question 9. We are now busy with the DBE 2015 paper. They say in the diagram, O is the center of the circle, and we know that BO and OD are drawn. The chords BC and O, the chords CB and DE are produced to meet in A, and BCD is equal to angle X. Now, if this here is equal to angle X, we know that the angle at the center of the circle is twice the angle at the circumference of the circle. And we know that if this here is a cyclic quad, then the exterior angle is equal to the opposite interior angle. Now, the acyclic quad is when a four-sided figure is drawn in a circle and the vertices fall on the circle. So that's a cyclic quad. And what are the theorems of the cyclic quad? Opposite angles are supplementary. Exterior angle is equal to the opposite interior angle. So why is E1 equal to X? And the reason is the exterior angle of a cyclic quad is equal to the opposite interior angle. And why is O1 equal to 2x? The angle at the center is 2 times the angle at the circumference. Okay, it is given that BE is parallel to CD. It is given that BE is parallel to DC. Prove that AC is equal to AD. So when will AC equal to AD? If the base angles are equal. So I've got to prove that there is equal to X. But I know that that is X. So if that is X, then this must be X corresponding angles, because we just said these two lines are parallel. And if that is X and this is X, then the sides opposite equal angles are equal, therefore AD must equal to AC. We can prove that by saying in 9.2.1, we can say that D1 plus 2 is equal to E1, which is equal to X. D1 plus 2 is equal to E1 is equal to X, corresponding angles, because EB is parallel to DC. Right. The next thing is that angle C is equal to angle X, and that is given. Therefore, we can say that AD is equal to AC, angles, sides equal, the sides opposite equal angles. Right, the sides opposite equal angles. And 9.2.2, we've got to prove that ABOD, we've got to prove that ABOD is a cyclic quad. Now we know that if that is X, then this here must be 180 degrees minus 2x, the interior angles of a triangle. Now, if this here is 2x, which is proven, and this is 180 degrees minus 2x, then opposite angles are supplementary. Therefore, it's a cyclic quad. So we can go in and say that angle A is equal to 180 degrees minus 2x, interior angles of a triangle. We can say that angle O1 is equal to, angle O1 is equal to 2x, and that we proved in 9.1.2. And because angle A plus angle O1 is equal to 180 degrees, therefore we can say that ABOD is a cyclic quad. Okay. We are now going to move on to the November 2013 paper. Once again, we're going to read the question. Once we read the question, we are going to make certain deductions, and we are going to look for the key words. So they say in the diagram, O is the center of the circle. So if O is the center of the circle, we know that the angle that it subtends at the circumference is 90 degrees. So if that is 56 degrees, then this here will be 34 degrees, because together they will be 90 degrees. If O is the center of the circle, then we know we can get radii, but that's not applicable. A line drawn from the center of the circle to a tangent is 90 degrees. That's not applicable. If O is the center of the circle, then the angle at the center of the circle is twice the angle at the circumference. That's 180, so therefore that is 90. And then nothing else will be applicable. They say GEH is a tangent to the circle. GEH is a tangent. That means if this here is 32 degrees, this here is 32 degrees, the tan chord theorem. Now, if this here is 66 degrees, then that also would be 66 degrees, the tan chord theorem. Right, so because this here is a tangent, we can apply the tan chord theorem to it. And also tangents drawn from a point outside the circle are equal in length. That's not applicable. The radius perpendicular to a tangent, that's not applicable. The first question is, we need to determine E2. Now we just said, now E2 is equal to 34 degrees, because BD, the diameter DB, subtends an angle of 90 degrees. DB subtends an angle of 90 degrees. If that's a diameter, that is 90. If that is 56, that will be 34 degrees. Now we want EBC. We want that whole angle there. Now, we know that the angle between the tangent and the chord is equal to the angle in the alternate segment. So that whole angle there is equal to 66 degrees. So therefore, that angle there is 66, so that must be 34 degrees. So EBC is equal to this whole angle there. We can say it's equal to angle E1 plus 2, which is equal to 66 degrees. And the reason is the tan chord theorem. And then we need to find angle F. Now, angle F is that angle there. But if that there is 66 and that there is 56, then we can find this angle here. And once we found this angle, we know opposite angles in the cyclic quad are supplementary, and we can work out F. So we can say that 66 degrees plus 56 degrees equals 122. So this here is 58 degrees, and then this here be 122 degrees, because opposite angles are supplementary. So we can first of all say that angle C is equal to 58 degrees, interior angles of a triangle, and then we can say that angle F is equal to 122 degrees, opposite angles of a cyclic quadrilateral are supplementary. Opposite angles of a cyclic quad is supplementary. If that is 56, then that must be 22, because opposite angles of a cyclic quad are supplementary. This here is a cyclic quad. So therefore, if that is 58, that must be 122. The other theorem that we need to prove is that if a line is drawn from the center of the circle perpendicular to the chord, it will bisect the chord. Then we're just going to construct AO and AOC, and we're going to prove these two triangles are congruent, and if they're congruent, and we're going to use 90 degrees, and that is equal to that because they're radii, and this is common. So we're going to use 90 degrees, hypotenuse and side to prove congruency, and if they're congruent, then AB is equal to BC. That is a formal proof, and it needs to be set out in the way that a formal proof is set out. Right. In this question here, we are busy with the November 2015 paper. Now this is a lot more difficult. It is pitched at a higher level. So let us work through the question from scratch. In the diagram below, triangle ABC is drawn in the circle. TA and TB are tangents to the circle. Now if TA and TB are tangents to the circle, then obviously that is equal to that, and if that is x, then this here would be x. The base angles would be equal. And if it's a tangent, we know the angle between the tangent and the chord. Angle to the tangent and the chord is equal to the angle in the alternate segment. And the angle between the tangent and the chord, if we look at the big one, is equal to the angle in the alternate segment. They also know that the straight line THK is parallel to AC. If that line is parallel to that line, then alternate corresponding and cointerior angles exist. And they say that A3 is equal to angle X. Prove that K3 is equal to X. Okay, now we know that there, angle between the tangent and the chord, is equal to the angle in the alternate segment. So therefore that is X. Now if that line is parallel to that line, then K3 must also equal to X, and that's what they want. So here we can say in 9.1, we can say that angle A3 is equal to angle C, which is equal to angle X, tan chord theorem. And we can say that angle C is equal to angle K3, which is equal to X, and that there is corresponding angles because TK is parallel to AC, and therefore angle K3 is equal to X. Right. And that's what they want. They want K3 equal to X. The next question. Right. The next question is prove that AKBT is a cyclic quad. We've got to prove that AKBT is a cyclic quad. Now this here is only a cyclic quad if if opposite angles are supplementary, the exterior angle is equal to the opposite interior angle, or if a line segment subtends equal angles on the same side. Now in this case here, TB subtends X and TB subtends X. So because TB subtends equal angles on the same side, we can say it is a cyclic quad. So here we can say in question 9.2, we can say K3 is equal to X, proved in 9.1. And we can say that angle A3 is equal to X, and that was given. Therefore, we can say that AKBT is a cyclic quad because TB subtends equal angles on the same side. The next question, 9.3, prove that TK bisects AKB. Prove that TK bisects AKB. So we've got to prove that there is X. Now remember, this here is a cyclic quad. Now if TK subtends X, then TK must also subtend X. So therefore TK bisects this angle. To prove that, we're going to do the following. We're going to say that angle B2 is equal to angle X. Then we're going to say that K2 is equal to X. That we already proved. K2 is equal to X because AT subtends equal angles, and then we can say B2 is equal to K2 is equal to X because AT subtends equal angles, and then we can say therefore K3 is equal to X, proven. Therefore, K2 is equal to K3, which is equal to X. Once again, B2 is equal to K2 because it is subtended by AT, and because that is equal to that, and that is already proven as X, that was equal to that, and therefore TK bisects angle BKA. The next question, 9.4. Prove that TA is a tangent to the circle passing through AKH. Right. Now, the circle passes through AKH. Do you see the angle between the tangent of the chord is equal to the angle of the alternate segment? Therefore, TA will be a tangent. Because that is X and that is X, the angle between a chord and a line is equal to the angle of the alternate segment, therefore that line is a tangent, the converse of the tan-chord theorem. So to prove that, we're going to do the following. We are going to say angle A3 is equal to X, given. K2 is equal to X, proven in 9.3. Therefore, we can say that AT is a tangent, the converse, reason converse of the tan-chord theorem. Okay. We are now going to do the last sum for the day. This here is the November 2014 paper. It says in the diagram, it says that AB and AE are tangents to the circle. Now remember, if they tangents to a circle from a point outside, they equal in length, so that is also equal to X. They say B and E respectively. BC is a diameter. So if BC here is a diameter and this here is a tangent, then that angle there formed is 90 degrees, because a line drawn from the center of the circle to tangent is 90, the radius tangent theorem. AC is 13, BC is X plus 7. They say in this case, give reasons why ABC is 90 degrees. That then we can say the radius tangent theorem. And then they want to know why is AB equal to X. Then you can say tangents joined from a point outside the circle. Tangents joined from a point outside the circle. And now we've got to find the length of AB. So we need to find x. So now we're going to make use of Pythagoras' theorem. So we're going to say opposite 90 degrees is AC. So we're going to start off by saying that AC squared is equal to AB squared plus BC squared. And the reason here is Pythagoras' theorem. And now we're going to substitute. Now AC is 13, AB is x, and BC is x plus 7. Let's substitute it in. So AC is 13 squared is equal to AB, which is x squared, and BC is equal to x plus 7 squared. So 169 is equal to x squared plus 14x plus 49. So we can say 0 is equal to 2x squared plus 14x, and then 49 minus 169 gives you minus 120. And now we're going to divide by 2. Right, let's just make sure about this. If we divide by 2, we're going to say 0 is equal to x squared plus 7x minus 60. Now the factors of 60 is 12 multiplied by 5. So we can find the factors. X squared is x multiplied by x. This here is 12 multiplied by 5 is 60. That's positive, negative. So x is equal to negative 12, or x is equal to 5. But because they say find the length of AB, and AB is x, therefore we can say that AB is equal to 5 units. Right. This now brings us to the end of the session for grade 11 Euclidean geometry.